Hello? 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 Hello?
Hello?
Yeah, I can
Hello?
hear you now.
Okay, have you been around all this while? I don't even know.
Not long ago.
Okay. Good morning.
Yes, so good morning.
Okay. So, I think in our last class, we talked about missing data. We also looked at how you can fill missing data with your mean. We also looked at categorical variables, and how you can convert them to factors if you have them in R, and how you can also try to work with them. So, today I'm going to be looking at data transformation. I don't know if you can still recall this thing. We did this in our last session. That was Box-Cox transformation. Can you still recall it? Box-Cox
Yeah, I know we did
transformation.
this.
Yes, so we did something on this. So this is the Box-Cox transformation. It used to transform a variable. We usually use it to normalize variable. When the data is not normally,
Uh, Screen save is not clear. Let me open my own.
we have two graphs now. Okay.
Yeah, I say it's not clear. Maybe it's
Okay. Are you
network.
seeing it well now? Is the network
I
possible?
think it's better now.
I don't know. Okay.
Not really very, but it's better than
Okay.
I think it's
So you can see we have two data here. We have original data. We also have transformed data. Original data and we have transformed data. So this data is not normally distributed, you can see. So we transform it to this one. At least this one gives us a close to a bell-shaped curve. So you can see that this one is different from this one because we just transformed this one. We took the log of this. So the Box-Cox is just you just use logarithm transform to transform a variable. That's what the Box-Cox does. So here's a function that was created to do the Box-Cox. You know, already talked.
I can't hear you. Hello?
So you can see here
I
we
was
have
not
our
hearing
function
you.
here.
I think the network is bad.
Okay.
I don't know if you're also recording.
Okay. Yes, I'm recording.
Network is
So here is the Box-Cox. Here's the Box-Cox transformation. Are you hearing me now?
yeah, but the screen. But let's continue.
Okay. Here's the Box-Cox transformation. Is used to transform a variable that is not normally is used to transform a variable that is not normally distributed to a normally distributed variable. So if you look at this now, we have function x comma lambda is equals to 0. So if lambda is not equals to 0.0, that means is your lambda. If it's not equals to 0.0, then this variable is going to be transformed like this. You're going to transform this variable by saying what? X raised to the power of lambda minus 1 divided by lambda. I don't know if you get it.
I
Hello?
don't get it too.
This is a formula that you're looking at.
Okay.
It's based on this particular formula. This is a condition. So this is a function we are creating. This function is from two arguments.
Okay, we are
X
creating a
and lambda.
function. Okay.
X is your vector type, while lambda is what? Lambda is a parameter.
But
This is the formula of Box-Cox.
okay. Are you there?
Yes, I'm there. So can you see it now? See what I was saying? When lambda is not equal to 0, this is the formula. When lambda is equal to 0, this is the formula. This is also what we are trying to put inside that particular R code. That's what we are trying to put. So if lambda is not equal to 0, this is the formula I use. X raised to the power of lambda. Here they used y, but it's still x minus 1. Can you see it? Divided by what? Lambda. Can you see it?
Yes.
Then what? Y lambda. When say what? Log of y. Here they use ln y. Ln y and log are the same thing. Natural log is also same as ln. So you can see here they got log what? X. So if your lambda is not equal to 0, then you calculate what your new variable like this. But if it is equal to 0, then this is how you calculate it. Then you return the new variable. I don't know if you get it.
If it's equal to 0, if it's equal to 0, then you use that log x.
If it's equal to 0. That's why you see this particular condition else. If this is not equal to 0.
Yeah. So that else means if it is equal to 0. Are you there? Are you there?
Yes, I'm there.
So the condition now, that means the else is when it is equal to 0.
Yes, when it is equal to 0, that's the else.
Yeah, but this what I even want to ask here, this curly bracket, I'm seeing many of them, so I'm trying to see where each of them covers.
It's condition. They use this for condition. If this condition is true, then you what? Calculate this. Else, you what? Calculate what? This is for condition. They call it conditional statements.
Yeah, I think, but some of them are supposed to be closed. It closes at some point. So that's what it closes at some point, and it also opens at some point. Right?
You said?
I mean those curly brackets.
I'm not hearing you. What do you say?
Can you hear me? Can you hear me?
Yes, I'm hearing you now.
Yeah, I said the curly bracket. I'm trying to see where it covers. I know that there are two that start.
This one is for this curly bracket for the function itself.
Yes.
Then this one is for the condition. This is it. We're having 3 curly brackets here. This is the first one for the whole function.
Yes.
Then we have this one for the if condition. We have this one for the else
but that one
condition.
Is
so there are 3. Okay.
That one now itself is even after the if. That's what I'm looking at. Okay.
Yes, that's it now. It's just like saying this. They're the same thing.
Okay, yeah,
like this, they're also the same
I've
thing.
seen it.
You just put it there so it's much more data. It's also the same thing. So this is a function for calculating Box-Cox. Are you there?
Yes, I'm here. Can go on.
Hello?
Yes, I'm here. We can go on.
Hello?
I can hear you.
What does this mean again? Can I still recall?
Which one?
Yes, what does this mean? What does this mean?
Is it that per MF row? Because I'm not seeing,
Yes,
I'm looking
yes,
at I'm
yes.
looking at the other, not this the slide. So that per MF
What does
row
it
is
mean?
used to how you arrange your chart, the graph. So it means for one
What
and
is
1,2
okay?
means
Then
one row, then 2 column. So
how
it's
many
going to
rows? How
appear
many
side by side,
columns?
like left to right. Can you hear me?
How many? Yes, how many rows? How many columns?
One row, 2 columns. For 1 to 2, if that is what is there.
Are you with me?
I'm not seeing your screen very
How
well,
many
but I'm
rows? How
looking
many
at the slide.
columns?
Huh? Your
Okay,
screen
so
is not
it's
clear,
the
but
network.
I'm only commenting based on what is on the slide. I'm seeing 1,2. And 1,2 means 1 row, 2 columns
Exactly,
for the
that was what I'm
chart.
saying.
Can you hear me?
So now, yes, yes, I'm hearing you clearly. So we want to build two histograms. One is using what the data itself, while the second one is using what box cox. This second one is in box cox. So we're having two histograms now. First one, second one. So we're going to be having one row, two columns. So for the first one now, we're going to use the hist function. So the histogram function takes a vector. Then I say air quality $ozone. Air quality $ozone. And frequency is equals to false. Then X lab is equals to PPB. And your main is equals to what? Original data. I don't know if you get it.
Yes. The S lab is
Hello, are you there?
the S. Can you hear me?
Yes, I'm hearing you.
Yeah, if to recall again, the X lab is the X axis. What the name of the X axis, right?
Yes.
Then the frequency equal to false.
So if we put frequency equals to false, what's going to happen to our graph?
That's what I'm trying to remember.
If we frequency equals to false, from the name frequency equals to, what does it tell you? I thought that sometimes we use frequency, sometimes we use what? Density. So frequency is equals to false, what will it show you?
Okay, frequency equal to false.
What will you get? Are you there?
Is it to get density?
Yes, you get density.
Okay.
So let's run this now and see. So can you see our data now?
So
So you
that's
can
just
see
the
our data.
difference.
These are
That
first data.
frequency, when it is true, it gives you the normal graph. The false is density.
Exactly. It gives you frequency. When it is false, it gives you density.
Okay.
I don't know if you get it.
Yes.
No. So now when you now do that, then the next one now is going to plot the box cox now, not just the normal variable that we have. The next one now, we're going to use it to plot box cox. So the next one is going to use to plot what? Box cox. Where is it? So here is it, box cox. So we're using the box cox function to return. When you put box cox like this, if you run it like this now, let's run it here. When you run it like this, okay, we have not run this function. Let's run it. Then if we now paste it here, so can you see it? When you run the what box cox, this is what you get. So this is how it is going to transform it. You can see that when I put air quality ozone now, ozone is different. Can you see it is actually different? air quality ozone is actually different. Can you see it?
I'm not even.
Can you see this is the initial variable?
Well, it's not clear, but what I'm seeing is that I'm seeing that the other one has a lot of numbers, maybe with decimal, right?
You said?
Your screen is not clear
You
at all,
said?
but I'm just like seeing like a kind of shadow. So I'm saying that I think the
Okay.
difference is that the other one is whole number, the other one have like some decimals after and is longer, right?
Yes. This one is the transformed one. Why this one is the initial variable itself?
Okay.
This is the initial variable. Why this other one is the transformed one? When that was transformed. I don't know if it's clear.
Yes.
Okay, then frequency is equals to what? Force. Also, now I can see the X lab. This is the title of the X lab log PPB. Then main is equal to transform data. So when I run this now, so you can see what we have now. So this is the transform data. This is one that was this is the original data. So all these ones that
whatever that
were
zero
low
that
before that
is
already become
okay,
high.
that zero is what is in that formula, right? I'm trying to
Yes,
relate it
that's what
under
will
the
make
formula
it.
where
You
you
see
have
it is
box
zero.
plot.
If it is zero, this one we to use. That's why I can see we have log PPB here. If it is zero, this is what it will use. That's why I see we have log PPB in this place.
That's if does it mean like if X if S is if the ozone is zero? Is that what it
You
means?
said?
I mean the air quality
I'm not
ozone.
hearing you clearly.
I mean the air quality. Like no, I want to relate to the formula. I
Can
want
you
to
come
relate to
again?
that formula. What's now the condition that this one now is meeting?
It's zero.
What I mean, if does that mean if
Once
the
you
air
give zero,
quality
then
ozone, I mean, what is the lambda here
I'm
now?
with
That's
you.
what
I'm
I'm
hearing
trying
you.
to say. Lambda is zero.
The lambda is zero. Once it is zero, this is the formula is going to use. Else, this is what it will use. You know, this is what they say not equals to zero. Can you see it?
Yes.
So, but once it is zero, this is what it's going to use. This formula.
Okay.
So now, here we plotted. Can you see here
Like,
we
sorry.
plotted box histogram. This
So
second
in this
one.
case now,
Okay.
yeah, in this case now, why did we use lambda as zero?
That's what I said, that it depends. You can either use lambda is a parameter. So you just try to
Okay.
demonstrate an example. You can use lambda is
Okay.
equals to zero, you can use lambda is equals to 1.
Okay.
Yes.
Okay.
So just like this place, the only difference here with this one is that here we're using box plot. We are not using what? We are not using histogram. So you can see this one now. Here we're using what? Box plot, not histogram. The former one we use what? Histogram. This one we're using what? Box plot. So it's just to show you the difference between the two. This is the normal transformation. This is the normal data, and this is the one with the box Cox transformation. I don't know if you get it.
Yes. So what we even this okay. I think I've seen using. I think that histogram we even explain it better when it is transformed. So the idea is to like transform it to become a bell shape, which is the normal distribution.
Exactly.
Okay.
Exactly.
Okay. Yeah, can go on.
Okay. So now the next thing that we have now is now there's a function for box Cox. No, sorry, there's a function that helps you identify the value of lambda. So which value should you use for a lambda? That question you were asking earlier on, that why did we use zero? So this way can determine which value should you use as your lambda. I don't know if you get it.
Okay.
So this is the function. If we run it here, so can you see it?
Which function are you running?
Possible values of your lambda is
Is it that mass? Which function are you?
this box. Do you know the reason why we put mass here?
Well, I'm not seeing what you are running. What did you run?
This place.
Initially. That one?
Yeah, this is what I run.
Okay.
Yes.
Because I'm looking at my own. Okay. This should be network. The network is really, really bad.
Seriously, it's network. I don't know what's happening.
I'm not saying what is on your screen. I'm just seeing shadows.
Seriously.
Yeah.
Sorry about that. Sorry about that.
Okay, go on. But I'm looking at my own slides, not the arrow codes. The slide, yeah. So I'm seeing mass. I'm seeing some dots.
So this mass is the package name. These are used to call a lab. If you want to use a function from a package, I've talked about packages now. Can you still recall? You want to use a function from a package without calling this. You don't want to call this because you're just using the function maybe once. If I do this now like this, I don't need to put this one again. I'll just remove it. Can you see? I'll remove it.
Okay.
Yes. But if I'm not calling that, then I need to. If I'm not calling this line like this, if I'm not calling it, then I need to what? I need to call this particular one, mass, then these two columns. So this will tell R that use the function under this particular package. I don't know if you get it.
Okay, yeah.
So now this is the boxcox takes your data. So if you look at it now, boxcox. So you can see it. So this thing I'm trying to explain here, this particular object. Okay, I understand. Okay. Now, this thing means you identify that what? This is the only variable. There is no independent variables. That's what it means, this particular piece. I don't know if you understand.
That which one is the only variable?
By the time I put this line, something 1, it means you identify that this is the only what? This variable is the only one. It's the only variable you are looking at. You don't have any other dependent variables or independent variables. That's what it means. So this will get you the appropriate lambda for you to use. If you look at this, we can see we have 3 possible values of lambda. And most of them are close to 0 point something. So 0.5 should be around there. So 0 to 0.5, you have the values of the lambda.
0.5 the values of the lambda, is it those minus 2 to 2? Or those lines?
No, this line here. This line here is the optimal lambda you are looking for. This is the optimal lambda.
Okay.
This line here.
Okay.
So, and you see they are between 0 and 1. And 0.5 is around here. So they are between 0 and what? 0.5. So those are the values of the lambda you can give. I don't know if it's clear.
So in this case, now, is it just those 3 lines?
You pick one of them. You pick one of them that are going to use. I don't know if you understand.
Yeah, no, we are not even seeing the value. So is it just to pick anything?
Yes, the values are not there. It's you that you can estimate what the values are. You can see that year to year 0 to 1. Why did half of year 0.5? So this value should be around 0.1. I can see you can give any values between 0 to 0.5 because you can see all of them fall on the line.
Okay, to use it as your lambda.
Yes, to use it as your lambda.
And once is that 0. Let's say 0.1.
You can give something like that because it falls in the range of the possible values of lambda that you have to give.
Yeah, I think in that place we say either lambda is 0.01 or when it is not. Okay, that means if we are using any value that is not 0, it means the other condition will not be fulfilled.
Exactly. I don't know if you get it.
Yeah.
So now we have what we now call standardization again. Standardization is where, that day we are talking about outliers. So this is where you use standardization. Now, if you look at this now, there's a function called scale. You use scale on the variable your variable, like if you look at, let me call this CO2. This CO2 was under which data? CO2 was under which data? Okay, let me do like this. I'm coming. Coming. CO2 should be under which data set? Let me see. Okay, I think this is the data set. Okay, this is it. So CO2 data set, $ CO2. I don't know if you get it. We are trying to scale this particular variable, this CO2 variable. Can you see it? When you scale it, the value is going to range from 0 to 1. I don't know if you get it. By the time, okay, are you seeing this CO2 data set? This one, this CO2 column.
Yes.
Can you see it? So when you scale this column, the values are going to range from 0 to 1. Such that when you take the mean, you're going to get 0. And when you take the standard deviation, you're going to get 1. So that's why it is called standardization. You want to make these values now. You talk about outliers that day. So these are your undo outliers. These values, you're going to make them range from 0 to 1. Let me show you. Use this function. Center means what? Your mean should be 0. And say scale is equal to false. So when you check these arguments now, let's check the scale. Can see. So center is a logical value or numerical like vector length equal to the number of columns. Then we have a scale equal to the number of columns. So when you run this now, CO2 data set.
There's A after CO2. Okay.
Okay, small letter O. Okay. Small letter O. So when you run it now, and I call Y, can you see the values now? When you take the mean of these values now, mean of Y, can you see you're going to get 0, 0.0 something, which is approximately 0. When you take the standard deviation, you're going to be getting 15.3153. So when you run this one too now, these one are two different things. Now if I run this again, and here now, if you notice the difference, here I made the center, the scale to be false. Here I made the scale to be true. So when I run this now, can you see I get 1? So if you don't want your standard deviation to be 1, then you give scale is equal to false. If you want the standard deviation to be 1, you give scale is equal to what? True. So this I can handle.
So what's the difference? Is it not the one that is 1 that is correct?
Or no. They're both different things. That's why I say scale. You can see.
So what are we now using the scale for now? For standardization now?
Yes, the scale is if you want your standard deviation to be 1. If you don't want the standard deviation to be 1, then you use what scale is equal to false. I don't know if you get it.
What's now the duplication between using it as like what's now the difference? Like if we want to look at how it will be on the data, what is the impact that we have on the data?
This one now is only fixing the mean. This one is only affecting the mean. Why this one is only affecting the the standard deviation and the mean.
Okay.
I don't even get it.
Yeah, but that first one also, there is some standardization that has already taken place, but yours that is affecting only the mean.
Which one?
Yes,
this particular one. This particular one, exactly. So this is the original standard deviation. If I say CO2 dataset, CO2, can you see that this is the original standard deviation? And can you see when we run this one, it was 15 we get. So this first one only affects the mean. Can you see it? It only affects the mean. It doesn't affect the standard deviation. So this is the original one. This is the original one. This is it. Initial one. This particular one. This is the initial one.
Yeah.
Yes. And this is the one that we. This is for the other first one, whereby we're only affecting the mean and not the standard deviation. Why this is the second one, whereby we're scaling both the mean and standard deviation.
Yeah, what is the mean for this one now? Okay, I'm seeing that's 13. There was not the standard deviation for this one.
For this one, this is standard deviation. Can you see one?
One. Can you see that? Then the mean. Okay. I can see it.
I don't know if it's clear.
Yes.
So relationship between pairs of numerical variables, we have scatter plot and correlation. Scatter plots and so we want to check relationship between variables. So we have what we call scatter plots. If you want to check relationship between two numerical variables, you use what we call a scatter plot. And how do you plot a scatter plot now? So based on our, let me just put this thing with CO2 data set. I thought it's like this now. Let's do it. Okay. I can still record that function we used to hold the data set. Was it width? Can I still record? So well, let's remove it. Let's just use the CO2 data set here like this. Then $sign CO2. Same thing to also in here. Same thing also in here. So when you run this, you get this. So when you run this is scatter plots. Relationship between what CO2.
You are using a different data set.
No, it's still the same CO2 data set. I gave the first column here. And I gave the second variable, second column here. So sorry, so to be temperature.
And the one they use here, what about the one they use here? Why didn't you use the one in the...
It's because we have not called the data set inside. You know there's a function we talked about that you call a data set. I think it was width or something like that we use. And I don't want us to be using that because it's actually going to be confusing when you're working with multiple data sets in your work. It's better you just use your $sign to be calling the data set.
Okay.
So, because if you are using 3 data sets in your exam now, you just be confusing them together. So just use your $sign to call your data set. It's better.
Okay.
So this is the relationship between what? CO2 and temperature. So it's going to be plotting CO2 against what? Temperature, as you can see. Any value of CO2, you plot it against temperature. So this is what we call a scatter plot. A scatter plot is used to show the relationship between two variables. Now to use a scatter plot for. I don't know if you get.
Yeah.
So we also have another formula.
This PCH equal to 20.
Yes, it's points, the size of the point. That's the size of your point. So for year 2,
whether I want it to be bolder or smaller.
Oh yes,
something like that.
Okay. Yes. So yeah, now
remove it, if you remove that PCH, it will still work, right? Maybe it will give you like the default.
Yeah, wait. To give you the default. Can you see? It's going to give you a lighter, something light.
Okay.
So this is another way of also calling. This is another way of also calling. This is another way of also calling your to plot a relationship between two. This is another way.
I'm not seeing the particular one.
This one.
Okay.
This is another way where you use this formula sign. You use this tilde sign. They call this tilde sign. So it's also another way if you don't use this approach.
My last exam, I suspected that I'm going to use it, and it's not there in the system. I couldn't find it. I just Googled it and left it there. I copied it from the internet because the
Sometimes
internet
you can just
they later offed it.
you can let sometimes if you don't see it on your keyboard, you can just do like this. Just check LM. When you check LM, you see it here. At the down in the examples, you should see it.
Okay.
See it here, see it here. So you just copy it from here inside your app.
Okay.
Yes, this is how you do it.
That this case now. Okay, maybe you explain it now. Because I'm seeing that the temperature or the position does not matter. Temperature is coming before the CO2.
This one is not a comma. It's a this thing.
Yeah, I know, but the previous
It
line,
doesn't
the
matter
previous
in this
formula.
scenario. It doesn't in this place. Yes,
Yeah.
it takes two. Yeah. It takes two.
We have CO2, we have
vectors.
temperature. Whether one will
It
be
takes
on
two
the
vectors.
x-axis, y, it doesn't matter.
Yes, if you
Y-axis.
put this one first, this one will be on the x-axis, as you can see. If you put that CO2 first, it's going to be on the x-axis. Can you see it?
So, and because they are not of the same scale, so I'm just thinking if it's going to affect your.
Yes, that's what I'm saying. If CO2 is first, it's going to be on your x-axis. But if CO2 is the second, it's going to be on the y-axis.
But
the first
it
one
affected the way the chart is now, Abi.
It as how? It's just going to flip it. So it's just going to flip the chart because the x-axis has become temperature, y-axis has become CO2.
Yes, I'm saying that means the point will be flipped also.
Yes, it's going to be flipped. It's going to be flipped.
Because why I'm asking, because I'm saying that it's different in line 141. So I'm just saying, is it because you are using that Tinder sign? Is that why the thing is?
Line 141 is still the same thing. Oh, this is it.
Eh?
Line 141 is still the same thing. This is line 141.
141 and 139. You know,
yes,
you've not brought temperature.
Thing.
So I'm not saying, is it because you are using that
this
sign?
One
That's why
because you are using this sign. The first thing that comes here, if you are using this sign, is your Y. If you are using this sign, is your Y.
That's what I'm asking.
Then followed by your X.
Okay, why the other one is the X before the Y?
Yes. I don't know if you get it.
Yes.
Then this is your correlation.
So both of them mean the same thing, right? I think
they both mean the same thing.
Okay.
It's all different way of approaching it. They both mean the same
Okay.
thing. Then we can also use this function called correlation. So when you plot this one, you get correlation value. I explained the correlation that time. The correlation ranges from 0 to 1. Sorry, from -1 to 1. So if you have from 0 to 1, it is positive correlation, as in above 0 to 1. If you have less than 0 to -1, that's a negative correlation. So for example, now in this case now, our correlation is 0.86. So it means there's a positive correlation between temperature and CO2.
So you said the negative correlation there is from
less than 0 to -1.
Less than 0
to -1. Correlation is, let me show you this.
I know you drew that line for me.
So can you see the line here? So can you see the line here? 0 means no correlation.
Yeah.
While anything from above 0 to 1 is positive correlation. Anything below 0 to -1 is negative correlation. So in terms of temperature and CO2, it means as temperature increases, CO2 is also going to what? Increase.
For which
one? For positive.
Okay.
Why for negative? As temperature increases, CO2 will what? Decrease. That's for negative.
Okay.
Then a strong positive correlation is from 0.5 to 1. I think you should go and check that video we did on correlation. I explained it.
Yes.
So 0.5 to 1 is where you have what? Strong positive correlation. Why 0.5 downwards close to 0 is what? Weak positive correlation. Likewise, when you go back to 0 to -0.5, you have strong positive and strong negative correlation. Sorry, weak negative correlation. Why -1 to -0.5, you have what? Strong negative correlation. That's how it works.
Yeah.
So you can see it here. So in our case now, our correlation is 0.8. So which means we have a strong positive correlation. As CO2 increases, temperature also what? Increases.
Okay.
It's clear?
Yeah.
Okay. So this is it. So you can also call, that's what we call a correlation plot. If you want to plot all variables against themselves, this is it. If you have 5 variables, now I don't want to be checking this one by one. You use what we call a correlation plot.
So when you have a line, the one on top.
You see it? Yeah, that's why we use this pairs. Pairs.
Okay, so if you want to,
is for use for multiple variables. Instead of picking it 2, 2, 2, 2, 2, 2, use for multiple. If you have like 10, you want to do correlation across each variables. So that's where you use pairs. Yes. I don't know if you get it.
Yes. So this pairs now, if you just call the pairs and or that pairs give you
on the data frame. We call it on the data frame. We call pairs on the data frame. We call pairs on the data frame.
So does it affect every other thing under, or that pairs is what is giving you those charts?
Is this pairs that will give you all these charts?
Okay, can we look at okay.
So when you see a line going up, it means positive correlation. When you see it coming down, it means what? Negative correlation. If you see it straight, it means what? No correlation. That's what it actually means. So some of these ones are scattered, which actually is also close to what? No correlation. You also see it scattered. It's also like no correlation also. You can see some of these are scattered. So
like if you see the one on the top left-hand side, you see those ones are positive, even though they are not straight, but they are moving like they are like straight line.
Yes. So right? This is temperature. Right? This is temperature. Yes, this is temperature.
Between temperature and year, those ones.
All these ones, because there's again themselves. That's why I don't see any value here. This first one is year.
No. I'm talking about those boxes that are close to them.
These ones.
By your left.
Yeah.
Yes, and the one on top too.
All these ones means no correlation.
Oh, because they are not straight like the other one.
Yes. But this one still even means correlation. But this one is year now. Year is not a numeric variable, so we cannot use year. But if you look at temperature, yes, if you look at this column is year. This column is temperature. This column is CO2. This column is TSI. Okay. This row is year. This row is temperature. This row is CO2. This row is TSI. This row is TSI. This row is CO2.
Okay. I've seen how you are reading.
When you say temperature against CO2, this is what you have. Temperature against CO2. Since temperature is in this column, CO2 is in this row. So temperature against CO2.
Okay, that's what it means. Okay, because yes. I was wondering how to read this. Okay, I get that.
You can now have temperature against CO2 here. Okay, you can see that the same thing. You can see that the same thing, but the same thing. So you can also have TSI against temperature is in this place. TSI against CO2 is this one.
So the CO2 can either be column or it can be in row.
Yes. That's why it's called a correlation matrix.
Okay. Could it be that the reason why we have those other two ways of where you have that where I was asking you put temperature first or you put it second?
No, this one is different. So this is a correlation matrix. So you are plotting all the variables. That one that we use just for 2 variables. They are 2 different in entirely.
So you know what I'm trying to read there? What I'm trying to read, you know that if you look, let's say you are taking only 2, temperature and CO2.
Yes.
If you check it very well, like what you explained to me now, if you see where if the temperature is on the column, on the column, on the row, while CO2 is on the column, you see that it gives you an answer.
Yes.
Then when temperature is on the column, then CO2 is on the row, it also gives you an answer.
Exactly.
So I'm just asking that which is that flipping you are talking. I don't know if it's it looks it makes sense that way, but I don't know.
Okay, so as I said that your columns is just the data and your columns is from year to TSI. Your rows is all from year to TSI. So that's why I see year against year. There's nothing here because you cannot have year against year. You can also have temperature against temperature. There's nothing here. You can't have CO2 against CO2. There's nothing here. So that's why, but when you go here, you see CO2 against TSI because TSI is the 4th column, CO2 is the 3rd row.
Okay.
I don't know if it's clear.
Yes.
So we have 2 types of, there's an argument in this correlation function called Spearman and Kendall. So Spearman is another kind of correlation. Kendall is another kind of correlation. So sometimes the values can be equal, sometimes they can be different. you have Spearman rank correlation, you have Kendall. So, but most of the times it's good you always use the Spearman rank correlation. It's always good to use the Spearman rank correlation.
Are you done? Wait till.
I'm coming. Okay. Okay. Is there any question?
You did explain that now, the formula now.
Which one?
You said they were the line 147.
Yes, that's what I said. That this one is a Spearman.
Okay, depending on the method you are using.
Yes, they're all the same thing. It just depends on the method you use. This one is Spearman. This one is Kendall.
And I see that both of them they have different answers.
That you have different values, but at times the Kendall can be. It depends on the kind of data you have. At times they can be close or the same. At times they can be different.
But it's advisable to use Spearman.
Spearman, yes, it's really good to use the Spearman.
Okay.
Yes.
So in 151, they call the data again.
You see?
151.
Yes, this is it.
No, like 151, yeah.
This is what you
What's that? Is it just to look at the data or what? We've done
this one is also the same thing we did. This matrix plots. But this time is now numbers. Can you see it? It's numbers now, not plot again. It's still the same thing.
Okay.
This is the function for it, COR. 5 for diagrams, use pairs. While for this data set, use COR.
Okay.
I don't know if you get it.
Yeah.
So this is what you have. It's the same thing here. You can see it's temperature against here, CO2 against here. Here you have what? Temperature against CO2 in this place. So temperature against CO2. You have TSI against what? CO2. So this is how you interpret it. It's just similar things to the plot. It's just that this time around we are getting numbers instead of the plots. I don't know if it's clear.
Yes.
The next thing that we have is apply. Is.NA equality, 2, so I already explained apply. Apply, you give your what? You give your vector. Then what did I say this number is? What did I say this number is? Under apply.
I'm looking at it. This applies is to remove a...
Apply a function on columns of a data frame. That is what apply is for. Apply function. We did it in our last class. Apply a function to columns of a data frame. That's what you use apply for.
What about this is.NA?
Yes, that's why I say we are just trying to this is.NA equality now. It's like trying to say remove all NAs in equality.
Yes.
Any row that is NA, remove it. So it's going to only apply it on the what? On the columns, on the values that are not NA. I don't know if you get it. Do you know what the apply is for? So I think we explained this last class.
Yeah, that's one. Yeah.
So you need to understand the apply because you'll be using it a lot. Apply and L apply. I've explained it last class. I said explained it in the class before last class. What's the 2 for? What's the 2 for?
You say apply and what?
L apply. I explained all of this in the last class. What's the 2 for in apply?
I think
I told you I use apply when you want to apply a function on columns of a data frame or rows of a data frame. And I told you I used to have 2 values, 1 or 2. So what is 2 for?
2 is for column.
Exactly. So when you want to apply, then the third thing will be your function. So when you run this now, you are getting total numbers of what n is. If you look at it now.
Because of the sum?
Yes. Because it's going to give you true or false. Where is it safe?
Okay.
Did they put it here? So this is the total number of missing value. You are saying is.NA equality. So if it is NA in each column, it will come out as what? True. If it is not NA, it will come out as false. And I told you that what? True is 1 in R, while false is what? 0. So when you apply sum, it's going to sum all the truths. That's why I get 37 under ozone. You get 7 under solar radiation. You can see for wind, temperature, and month and day, there is no missing values.
Okay, for the column. Okay. Yes. So you said the other one is if you put 1, then it will not be for row.
Yes.
But the row now does not have they don't have like name now. How will it not be since this one is showing columns?
For the row. It's just going to show for each row. Can you see for each row how many? Can you see these are the number of rows we have for each row? How many missing numbers are there? For each row, you can see the number of missing values there. So it's just the same thing. You are applying for 2, you are applying on columns. For rows, you are applying on only what? Only rows. You are using 1.
Okay. Yeah. So what if you want to check all the false?
If you want to check all the false, you now see what? Let me see it here. You use not is.ne.
Okay.
Can you see it now? Not is.ne. That's what you use.
Yeah, the values are even more. Yeah, okay. Yeah, see the other ones, they are even the same self because they don't have missing values.
Good. You see, so you can see what you are seeing. Okay.
Time it's fast spent, so I didn't even check.
So should we stop here? Or?
Yes, let's stop.
Okay. Okay, no problem. So we'll meet tomorrow. Tomorrow we meet by maybe 2.
Okay, that money will not work for you.